Okay, so hopefully you've had the experience now of watching transverse waves on ropes, very similar to this picture here where we have one student who is letting the rope sort of drape or dangle over a metal rod, and the weight is actually what's providing the tension in the rope. And so I'd like to go over a sample calculation with you so that you make sure that you know how that you can ensure that you're actually doing this correctly. And so I'll call this kind of as an example solution here. And the key ideas that we have here are that the mass per unit length of the rope is going to be just whatever the mass of the rope is divided by how long it is. This is something that we computed in class together, and I'll go over that calculation for a specific example. We then calculated the wave velocity based on the tension, that is to say, how much weight have we actually put on this rope here. Notice that if this person were to sort of try to pull back and forth, it wouldn't really change the amount of tension in the rope, because it's really this weight that's actually doing the pulling. And that can be calculated by basically taking the mass of this thing and then multiplying by essentially 10. And so you can see that down here. We'll just use G equals to 10. So for example, a 1 kilogram weight would be equal to 10 newtons. A 2 kilogram weight would be equal to 20 newtons, and so on. If we had a half a kilogram, 5 newtons. So let's see here. Finally, we're going to compare this all in our sort of part C of our measurement here. We're going to compare actually to the wave speed and that we actually measure. So we'll give the wave a little flick, and then we'll look at how long does that wave take to travel all the way down the rope and then all the way back. And since it's a round trip, we're going to have twice the length of the rope. So if here's a little wave pulse and it's going to here, and then it comes back, if this is that total length L here, it has to travel twice L. So in other words, if you remember, distance is equal to speed times time, that distance is actually equal to 2L in this case. So if we solve for the speed here, we'll get 2L divided by the time that it takes, or in other words, we call this as the period that it takes to go there and back. Okay, so that's the setup, and we're ultimately looking to, hopefully, this speed that we calculate here from this formula should match up to the formula that we measure here. So these two should be the same as each other, we hope. Okay. So the first question is, what is our mass per unit length? This one is straightforward to calculate as long as you've measured what the mass of the rope is. And so we measured mass of the rope in this latest class that we did, although we might do it more exact next time. We guessed that it was about half of a kilogram. Okay, so we said 0.5 kilograms, or in other words, 1/2 of a kilogram. And the length we saw was 100 feet, which is approximately 30 meters. So I said 30 meters and half a kilogram. And if I put those two pieces of information together, this mu, which is mass per unit length, is going to be 1/2 of a kilogram divided by 30 meters. And if I bring that 1/2 down, I'll see it's 1/2 times 30, which is 60 kilograms per meter. And if I remember, 1/6 is, I'm sorry, 1/6 is actually about 0.17. So that means 1/60th is going to be approximately 0.017. So I'm going to put 0.017 as my mu. You could always at this point put this into a calculator and then just write down the result. It's going to be my mass per unit length. And notice how if I change the length of the rope, is it going to actually change is it going to change the mass per unit length? Well, you might think about that and say, well, maybe it would, but the mass would increase, it would get heavier, but it would also get longer by the same amount. So that, therefore, changing the length of the rope is not going to change the mass per unit length. That's an intrinsic property of the rope. Okay, so now that we've got mu, next thing is that we have to figure out our tension. Well, the group that I took the data from for this example used a water bottle, and they used a water bottle that was 0.5 liters. And it turns out that 1 liter of water is equal to 1 kilogram, which is kind of a nice little thing to know, actually. And so that means half a liter is going to be equal to half of a kilogram. And according to what we were saying earlier about kilograms to newtons, that means that if you multiply by 10, you'll get 5 newtons. So 5 newtons then would be the tension that's in the rope. So in other words, this rope goes over the little dowel thing, and then is attached to, in this case, a little water bottle. Here's my little crappy drawing of a water bottle, and it has some water in there, and that's kind of dangling down, and that is going to be 0.5 kilograms, which is approximately 1 pound. Okay, so let's use these two numbers then. So we have a mu, which is 0.017, and we have a tension, which is 5. So if we use this formula here, we'll do square root of 5 divided by 0.017. And if I put those numbers together, I'll get 17.3 meters per second. Don't forget to take the square root. So if you did 5 divided by this, then you have to also take the square root. We'll get 17.3 meters per second. And now we need to actually do a measurement. So the group took several measurements, and they measured a total period, the time that it takes to go there and back, of 1.50 seconds. So if that's true, then the speed is going to be twice the distance traveled, and that distance, they had 50 feet, or in other words 15 meters of rope, divided by 1.5 seconds. So you notice we have a meters per second now, and so that's 30 divided by 1.5, or in other words 20 meters per second. So they got 20 meters per second. You can say 20 or 20.0, depending on how well you think that you actually measured it. Now we need to just make a comparison here. So it looks like the measured speed is a little faster than we had maybe predicted, right? So maybe there was some error in their measurement. Maybe they measured the time to be a little bit shorter than it actually was, something like that. So when we do that here, let's try to calculate the percent deviation here. So the percent deviation is we take the measured result, which is going to be this number, minus the theoretical result, which is this 17.3, and then we're going to divide by 17.3 and then take and then multiply by 100 to get a percentage. So in other words, I'm going to take 20 minus 17.3 over 17.3. I'm going to do this on a calculator. I'm going to open up my little calculator here. I'm going to take the number 20, 20 minus 17.3 divided by 17.3. That gives me 0.156. Now to multiply this by 100 to get it as a percent, so that means that I'm off by 15.6%. And we're actually to the higher. If it was lower, it would be a minus sign. So for example, if we got 15 meters per second instead of 17.3, we would actually get a minus sign on our percent deviation. So in other words, we're 15% off from the result. By the way, you might be wondering, well, what number would be like to give me perfect agreement? Well, that would be if the period was exactly, if we took this formula here, in other words, that speed is equal to 2L divided by period. If we solve for period and said 2L over V, we could plug in this theoretical result in here for V, and we would take 2 times 15 divided by 17.3 would actually give us 1.73 seconds. So that's what we should have measured if it was absolutely, if we were spot on with the theory. But a lot of times theory and experiment don't always match, and there's good reasons for those, and we can explore and try to figure out why those things maybe didn't work. So for example, maybe we didn't get the mass per unit length right in the rope, and we need to recalculate that. Or maybe there's something about our model that doesn't really describe our experiment. So nonetheless, a 15.6% agreement is really nice, and most groups got somewhere between 10% all the way out to about 50% differences, and all those would be about reasonable. Now, the next part asks to actually make measurements that would be for a different tension. And so if we look back to our formula here, speed is square root of tension over mu. So that means that if I wanted to make the tension higher, the speed should also be higher. And many of you saw that But what's interesting is that if the speed becomes, if the tension becomes twice as high, then the speed doesn't actually become twice as high. It becomes 1.4 times as high because the square root of 2 is approximately 1.4. Okay. So what would I have to do to the tension if I wanted to make the speed be twice as much? Well, I'd have to multiply the tension by a factor of 4 because the square root of 4 is 2. Square root of 4 is equal to 2. So in other words, that's why I said it takes 4 times the tension to make the speed be increased by a factor of 2. So that's why we actually had to make a big change in the tension in order to measure a discernible difference in the speed. So, for example, if the tension became 20 newtons instead of the original 5 that we had, we could expect a speed to be approximately equal to about 35 meters per second. In other words, the time became shorter by a factor of 2. Does the wave invert when it hits the end? Well, actually, it turned out that in the experiment it was a bit difficult to measure this, and so I'd like to actually just bring up a PhET simulation here to PhET, and then what is it? Let's see, wave pulses or wave on a string. PhET wave on a string, and I think they just open up this simulation here just to take a look. Oops, I don't know what just happened. My goodness. Okay, here we go. And if we take a look at this here, I'm going to make it be a fixed end, just like our experiment. And if I go up, you notice that it inverts. I'll make a little pulse here that makes it maybe a little easier. So here's my pulse. And on the way back, it becomes down. Let me turn off the damping here just to really see it very nice and clearly here. So in other words, when the pulse gets to the edge, it has nowhere to go, and so it has to go down, coming back, and then it has to go up, coming back up, right? And so this is an important point because when we start to oscillate, we see that the waves that are going backwards and forwards actually are beginning to interfere with each other. And so this is actually going to create what we call as standing waves. And where, in other words, where maybe one point on this actually doesn't move, but another point goes up, down, up, down. And this is, in fact, what a guitar string does. And so this is kind of getting us ready for our next inquiries, which is to look at how do strings vibrate and produce sound. So does the wave invert when it hits the end? Yes. Does the wiggling the rope up and down faster change the speed of the wave by very much? And so you could have experimented around with this a little bit. The other thing that we can do is go to the simulation again. And this time I'm actually going to just say no end, just to try something here. And I'm going to do manual. And if I do like this, you can see how long it takes. And if I go up and down, it also goes at the same speed. And this is something that we had some experience with now in our simulations earlier, was that if you jiggle it really, really fast, or you just jiggle it slow, all of those waves travel at the same speed. So in other words, it's the tension in the rope that matters. It's not actually the rate at which we jiggle something up and down that affects the speed. So the answer to this is no. The last part is to try jiggling the wave up and down at regular intervals. And so hopefully you found that if you jiggled it up and down, that you could make the rope kind of go up and down like this. And so the middle part's going up, down, up, down, up, down. And if you jiggled it faster, you could get something like this, where these two lobes, where one part's going up, down, one part's going up, down, but right in the center, there's not anything happening. And then finally, if you wanted to go even more, you could find that you could get maybe 3 lobes, or 4 lobes, or 5 lobes, just by jiggling faster and faster. So these ones are all higher frequency, so more frequently to get higher modes. In other words, the more modes, this is n equals to 3 mode, n equals to 2, and n equals to 1 mode, that the higher the frequency you go, then the higher mode number. Lastly, this question is asking just again a reiteration of, is this a transverse or a longitudinal wave that we're studying? Well, since the wave pulse, if this is our rope here, the direction of the wave speed is this direction here, or that's the direction of the velocity, if you want to say. whereas the motion of the rope material itself is actually, in this case, up-down, whereas the motion of the wave is from left to right. Now, some of you also had this experience of wondering if the wave is, if I'm jiggling the rope left-right and watching the wave go forward, does that make it a longitudinal wave? And the answer is not quite, because you can jiggle this rope from side to side like this, and the wave can still go across this way. The only point is that the motion of the particles you need, or in other words, the material of the rope, if it's moving perpendicular to the motion of the wave, then it's still a transverse wave, even if it's up-down or left-right, because we have to think about what that is with respect to where that wave is actually moving. So anyway, that's the worksheet for our transverse waves, or waves on a rope, and hope that was informative, and I hope that you have a good day.